So let's get started on today. Today we're going to go over actually measures of it's measures of position, but it's really measures of spread. I don't know why they call it that. We ended chapter or section 3.2 on, let me get to the right page just to make sure I'm not forgetting something. Yeah, 3.2 is measures of spread. We ended on finding the standard deviation in our we ended on finding the standard deviation in our TI calculator, which is great. I found some other cool things we can do in the TI today that I'm going to go over. So if you have that handy, I would bust it out now. So I'm going to switch over to my document camera because I've got to write some stuff. Hold on, give me a second. Where is that button? There we go. Boom. Okay. It'll focus here in a second. Okay, so first we're going to start with the empirical rule, okay? The empirical rule, which is on page 121. Actually, that's an I. The empirical rule. And what the empirical rule says is, first off, you have to have bell-shaped data for this to work, okay? When and I'm going to just read off what it says on page 121. When a proportion or population is important, okay? Population, not sample. When a population has a histogram that is approximately bell-shaped, then 68% of the data will lie within one standard deviation of the mean, 95% will lie within two standard deviations, and that's all it says, actually. It says all or almost all the data will lie within 3 standard deviations. So I'm going to stick to the first two, okay? So let's look at this. It's saying if we have this data and we line it all up and it winds up having this nice bell-shaped look, which, remember, nice bell-shaped look means the mean and the median line up right about in the middle, okay? Lines up right in the middle. And if this data lines up right there, so we've got the mean down here. Remember, it's population. We use that symbol for population mean, okay? That mean is right in the middle, or really close to the middle. The empirical rule says, hey, now this is kind of one of those gray areas in math too, right? It's not that it always happens. It's just a nice estimate of when it happens, okay? It says within one standard deviation, we'll do a little, that's right there. With one standard deviation, we have 68% of our data, okay? We can assume 68% of our data lies within one standard deviation. Now, if you wanted to look at this, that spot would be the average, the mean, plus one standard deviation, right? This spot would be the average minus one standard deviation, okay? So I'm going to make up some data. Let's say we looked at, I don't know, if we looked at average test scores again, okay? And we'll do some like national test score. So we have a ton of data, okay? We looked at the average test score for some like collegiate entrance exam. It's not a 0 to 100 thing. It's just based on numbers. And it turns out our population mean for this test score is 47.5, okay? So our population mean for the test score is 47.5. And our standard deviation, now guys, I usually write standard deviation with like this. It's how I was taught. So I'm going to try to go kind of back and forth. I shouldn't go back and forth. I shouldn't keep it consistent, okay? But it turns out the standard deviation winds up to be 4.3 units, okay? And we're going to assume this test distribution is nice and bell-shaped, okay? We don't know what it looks like, but we've got a nice and bell-shaped distribution for these test scores. So what this first part of the empirical rules is stating says we can assume roughly 68% of test scores lie between, now this is where we have to find the lower end and the upper end, right? For this lower end, we've got to subtract these numbers. So we're going to say 47.5 minus 4.3, which winds up being what? 43.2, right? So we can assume roughly 68% of test scores lie between 43.2 points. And then we need the upper, right? Well, the upper we're going to add 47.5 plus 4.3, which winds up being, what's that? 51.8. So 51.8 points. Attach units to this, okay, guys? Make sure to attach units to let everybody know kind of what's going on. So now, the empirical rule, I'm going to go over this again, kind of now that we have it written. We've got these test scores. All we know is that the mean, the population mean is 47.5. We know the standard deviation is 4.3, and we know it comes from this nice bell-shaped distribution, okay? So because it's from the population and we know both of these, and we know the distribution is nice and bell-shaped, we can assume roughly 68% of our data, of our test scores, lies one standard deviation above the mean and one standard deviation below the mean. So 68% of the test scores lie between 43.2, which is one standard deviation below the mean, right? There's the mean minus one standard deviation. And the adding that gives me 51.8 points. So one standard deviation above the mean would be 51.8 points. Okay, so roughly 68% of our data lies between 43.2 and 51.8. Okay, so if your kid goes out and takes this test, or you go out and take this test, and you make a 50.8. So if you make a 50.8, you're kind of in this bucket, right? You're in this middle standard deviation bucket. You were one of these 68% people, right? Now, there's a few things that go with this, though. If this is 68%, if we take 100 minus 68, that's going to be what? 32. So I know 32% of my data lies in these tails. These are called the tails of the distribution, okay? Now I've got to split it up, right? Because 32%, these two have to add up to 32%. So this means 16% is here and 16% is down here, right? So what else? Some other things we can kind of get from this data. 16% of test scores will be above. Now for us, remember this is 51.8. 51.8 points. Okay? So there's only going to be 16% of our respondents that actually make above a 51.8, right? Because that's the upper one standard deviation. I mean, if you want to write this on there, you're more than welcome to, because we're going to use this example. Okay, so this is 47.5. This would be 51.8, and this would be 43.2, right? That also means we can assume roughly, I should say roughly, 16% of test scores will be below. Now, not 51.8, but 43.2. Okay, so 16% of test scores will be below the 43.2. That's what we're saying right here. Okay, questions? I'm going to go on now to the 95% example. So the second part of the empirical rule for this book says 95% of our data is going to lie within 2 standard deviations, okay? So if we looked at another example, we've got this nice bell curve, right? And we're right there in the middle with the mean. If we go up 2 standard deviations, so right here, you can see there's a lot more of the population going on, right? So this would be mu plus 2 standard deviations, and this would be mu minus 2 standard deviations. But we can expect 95% of our data to lie within 2 standard deviations. If we're coming from a population that is normally distributed, I say that's got this nice bell curve to it, okay? So now think about this, 95%, that means it only leaves us 5% for the tails. So that means each tail has 2.5% of data, right? And look, this adds up to 100%. So all of our data is represented. 2.5% is going to be below whatever this number is, right? 2.5% is above, but 95% of our data lies between. So I'm going to steal the example that we just did, but now do it with 95%. So remember, our average for this test, this population test, was 47.5, and our standard deviation is 4.3. So if I want to get the 95% kind of difference going on here, I'm going to take the 47.5 and I'm going to add 2 times 4.3, right? I'm going to be super lazy and use my calculator on my phone. Boom, 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 boom. So 47.5 plus 2 times 4.3, I get 56.1. So that means this upper part is going to be 56.1. And then the average we know is 47.5. And now we've got to subtract it, right? I'm going to do that above. So 47.5 minus 2 times 4.3. So 47.5 minus 2 times 4.3. Get 38.9. Well, let me check something real fast. Yep. So 38.9. Okay, so what this means now, though, is we can say, we can assume roughly 95% of test scores lie between 38.9 points and 56.1 points. Okay? Pretty straightforward. Now, if we want to add the other parts to this, like we did the last one, hold on here. Yeah, we can also say that, 2.5% of tests are above 56.1 points. Hey, you know what? If you take this test and you make a 57, you might think you did horrible, but you've got to look at it as a percentile, right? As a percentile, though, you did great. I mean, you scored in the top 2.5% if you made a 57, right? Anything above 56.1, you'd say you were in the top 2.5%. And then, 2.5% of tests are below 38.9 points. So if you made under 38.9, say you made like a 37, you would say that your test is in the bottom 2.5% of test scores. Okay? That makes sense? Hopefully that helps. This is one of those things where I feel like students, sometimes it's just hard to grasp because of how the question's asked. But if you go back to kind of graphing it, it always helps. Look, in statistics, drawing a picture will always help. Okay? So if we look at, let's find an example that they give. Oh, okay. I don't like that they gave a sample because this is supposed to be from a population. They even said that it was from a population, right? Yes, they did. Okay, anyway. And let's just kind of follow their example, 3.18. It's at the bottom of page 121. Now it gives us a table. I'm not going to make put the table in or anything like that, but we learned from the last video, or the last lecture on how to find standard deviation from a list. So what they did is that it says table 3.8 represents the percent of the population age 65 and over in each state and District of Columbia. Figure 3.8 represents a histogram of these data. Compute the mean and standard deviation and use the empirical rule to describe the data. So notice on the next page, on page 121, here, you don't have the book out. I kind of, no, it's not this, but that's fine. Page 121, you can see here that this is a nice histogram, right? I know it doesn't look nice because it's real data, but this is pretty good for a histogram. Like over here, or I should say bell-shaped. Like over here is a good example of skewed data, right? We don't have this nice meat in the middle. We have all the data kind of pushed to the left, which means we're right skewed, right? So if we go back over here, we've got this nice histogram and made a nice bell-shaped distribution. And then we pop it in our calculator and we find out that the average, because this is a population, right? It's every state. The average is 13 point, I'm going to round it to 25. So 13.25 is the average percent population over 65. And then it gives us the standard deviation. Now we need the population standard deviation, which is 1.68 if we round it. Okay, 1.68. Okay. So now, because we come from this nice normal distribution, we know the standard deviation, we know the mean, we can use the empirical rule to make some assumptions about these states. So what I'm going to do first before I do anything, because we're using the empirical rule, is I'm going to just draw it out. I've got the mean in the middle, right? 13.25. Okay. And I know one standard deviation up, and I'm going to have to get two standard deviations up as well. But I know one standard deviation up, I need to add these together, right? That's going to give me one standard deviation up. So I'm going to take my calculator. I'm going to do this the lazy way. 13.25 plus 1.68. That gives me 14.93. That's one standard deviation up. Now I'm going to do one standard deviation down. 13.25 minus 1.68. 11.57. I know that 68% of my data is going to lie right there. Okay, I mean, you can go all the way up if you want, that's fine. I know that 68% of my data is going to lie within 11.7 or 11.57 and 14.93. Now let's do the next level with this as well. We'll use a different color so it's kind of easier to see. It's just a totally different set. Now I've got to add 13.25 plus 2 standard deviations. So plus 2 times 1.68. And you wind up with 16.61. I've got to go 2 standard deviations down here. So 13.25 minus 2 times 1.68. And I wind up with 9.89. So right there. So I know that 95% of my data lies within these 2 standard deviations. So between 9.89 and 16.61, I've got 95% of my states. So roughly, I mean, 95% of my states would be what? 50 times 0.95. So about 48. About 47 to 48 states should lie between there. Okay. Okay. So let's get to the questions, actually. Or what were the questions? Oh, it says, oh, it just says use the empirical rule to describe the data. Yeah, so I guess I've done that already. But it says, yeah, we can assume that 68% of states have a population Oh, okay, hold on. 68, how would we word this? 68% of states have a population greater than 65 from, let's think of how we word this. This is a goofy one because it's like a percent within a percent. Okay. Yeah, they worded it. I'm just stealing it from the book. I'm having trouble wording this because it's a percent of a population and a percent of the number of states. So they said that we can include the percent of population above 65 is between 11.57 and 14.93 in approximately, I said roughly, they use the word approximately, it sounds fancier, approximately 68% of states. Okay. And then if we want to say the percent of the population above 65 is between 9.89 and 16.61 in approximately 95% of states. Okay. If you want to describe the data. Whew, I don't like that example because of the percent inside the percent and blah, blah, blah. That's not the best example. But do you guys have any questions? So let's do their other example, okay? Because I kind of like it better. It's back to test scores. This is example 3.19, says using the empirical rule to describe data sets. So then they just tell us, they say, hey, look, a large class of 200 students took an exam. The scores had sample means of 65 and sample standard deviations. Now remember, we use an S for sample standard deviations of 10. The histogram is approximately bell-shaped. Now, look, we're not supposed to use the empirical rule for this because the empirical rule is for populations. But I guess your book forgot that in one page already. So we're going to assume it's okay to use for this sample because it's big enough. So it says part A, find an interval that is likely to contain approximately 68% of the scores. Okay, well, I'm going to draw again because I just freaking love drawing. Okay. So in the middle, I know we've got 65. These numbers are going to be a lot easier, right? If I go one standard deviation up, I'm at 75. And if I go one standard deviation down, I'm at 55. And I know from the rule, this would give us 68% of our data, right? So therefore, for part A, I would say that the interval would be between 55 and 75. And your book states that it is likely that approximately, if you want to say roughly 68% of our data you can say tests because we're talking about tests, right? Lie between 55 and 75 points. Points. So roughly 68% of our tests lie between 55 and 75 points. So if I gave this test, I could expect really the majority, 68%, right, to lie above 55 and 65 or 75, between 55 and 75, I should say. And then it says approximately what percent of the scores lie between 45 and 85. Well, I'm going to draw this out again. So this is part B. And draw this out. And I know 65 is in the middle. I go up one, I'm at 75. That's not what they want. They want 85, right? I go up one more, I'm at 85. And then I go down one, I'm at 55. That's not what they want, though. They want 45. So notice in this example, they go up 45 or up 2 standard deviations and down 2 standard deviations, right? So that means 95% of our data, roughly 95%. Guys, we need to be careful because we need to understand this is roughly. This is an estimate. It's just kind of a, it's an estimate. That's all it is. We can't say that it's exact because it's not true. It's not going to be true all the time. Okay. So it's, roughly, well, actually, I think for this one, they even approximately what percent. So you can just say 95%. Yeah. Because that's all they asked. It's likely that 95% of the data is, between 45 and 85. So if we gave this test, we can expect about 95% of our data to lie between 45 and 85 points. Okay. Any questions? I know it's only 3 of us on here today, which is fine. Any questions about that empirical rule? It really just all goes back to, I kind of this one. This is a better one, right? 68% lies within 1 standard deviation. 95% roughly lies between 2 standard deviations. And it's not perfect, okay? That's the algebra part. It's not perfect. Okay, next we've got Chebyshev. So the Chebyshev inequality, this is another approximation, but with Chebyshev, you don't have to have a normal distribution, okay? Now, this is on the very top of page 124. Chebyshev inequality. Now, the Chebyshev inequality really, it doesn't have to be linear. I'm not linear. Oh my gosh, it doesn't have to be bell-shaped, and because of that, it's really set in a different way. It's set in an at least way. So we're at least so many standard deviations between the mean. Okay, or at least a % of our data is within so many standard deviations of the mean. Now, the inequality looks like this. First off, we have to talk about this. Is any data set, the proportion of the data will be within k standard deviations of the mean is at least 1 minus 1 over k squared. Okay? So 1 over k squared. Now, k is the number of standard deviations. So we're going to talk about how we're going to word this. And we're going to use what they use first. Typically, you use 2, right? So if I did 2 standard deviations, we'll see right away how this is different than the empirical rule. We use 2 standard deviations. We get 1 minus 1 over 2 squared. We get 1 minus 1/4. So we get 0.75 actually, right? Now, I'm going to think of this, though, as a percent. This is 75%, okay? So k equals 2 corresponds to 75%. And what that means, and I'm going to read it just straight out of the book, and I'm going to write it down, at least 75% of our data will lie within 2 standard deviations of the mean. So at least 75% of our data will lie. Now, we know if we're normally distributed, 95% do, right? So if we have nice bell-shaped, we don't just have 75%, we've got 95%. So the higher the nice, beautiful picture of a bell curve happens, then we know the higher this percentage goes, okay? But no matter what, we can say that 75% of our data will lie within 2 standard deviations. So let's look at 3 then. If we did k equals 3, if we wanted to know what percent of our data lies within 3 standard deviations, I'm going to do the same thing, 1 over 3 squared now, right? So 1 minus 1/9, which turns out to be, and I'm going to cheat a little, it's like 88.8. We'll say that. 0.8, I think it's 0.8 repeating. So 0.89 repeating. That doesn't matter. In the end, it winds up being 88.9%. Okay, 88.9%. So with 3 standard deviations, we can say at least 88.9% of our data will lie within 3 standard deviations of the mean. So no matter what now, so empirical rule is with nice normal bell-shaped distributions. Chebyshev, though, you don't have to have a nice normal distribution. We can just flat out say, hey, no matter what, 75% of our data is going to lie within 2 standard deviations, and 88.9% is going to lie within 3 standard deviations. It's kind of neat. Okay. I hate to say that this is just kind of a neat thing to know. We aren't going to use it again, but it's going to pop up in the homework and it's going to pop up on the test. Okay. And I'm not necessarily worried that you memorize it because you're going to be able to use your notes and stuff for the book. It's explaining it that you're going to have to understand. Okay. You're going to have to understand that how to explain the Chebyshev, in that once you know that it gives you the percent of that you're within, at least the percentage that you're within the number of standard deviations. Okay. Questions? Okay. So then let's look at the coefficient of variation, which isn't a big deal, but your book, for some reason, this author enjoys talking about it. So we'll talk about it. Coefficient of variation is at the very top of page 125, and it's just found by dividing the standard deviation by the mean. It gives you a relativeness of the standard deviation to the mean. I know it sounds goofy, but we'll look at an example. Hopefully it makes a little more sense. But the coefficient of variation is just CV, and you take the standard deviation and you divide it by the mean. Okay, you just take the standard deviation and you divide by the mean. So I'm going to use their example there on page 125. It says the National Weather Service records show that over a 30-year period, the annual precipitation in Atlanta had a mean of 49.8 inches with a standard deviation of 7.6 inches. Okay, so if I wanted the coefficient of variation, I would just say this is 7.6 divided by 49.8. And notice the inches will cancel. So you wind up with 0.153. Okay, I'm going to keep reading. And the annual temperature for Atlanta during that time was 62.2 degrees Fahrenheit and a standard deviation of 1.3 degrees Fahrenheit. Okay, so therefore, if we wanted to find its coefficient of variation, we would say that's 1.3 degrees Fahrenheit over 62.2 degrees Fahrenheit. I think you put the degree over here. It doesn't matter. These are both going to cancel, and you're left with 0.021. Oh, that, yeah, 0.021. So here's our 2 different coefficient of variation. And what this means is that this ratio is larger. So the ratio, when you compare the rain to the standard deviation in the population, is higher than when you compare it to the temperature. Okay, when you compare the mean. I'm not that worried about it. It's an easy few points to make on a test, and it's really easy to find in the homework, okay? Your book even says the CV for precipitation is larger than CV for temperature. Therefore, precipitation has a greater spread relative to the mean, okay? So if we looked at the actual average, what's going to happen, this tells us if this was like a nice bell shape, this tells us that this one's going to be larger, so it's going to be a little flatter. Now, this is drastically flatter. Where when we looked at this percentage, it's going to go around the mean a lot tighter, okay? Flatter distribution, tighter distribution. They're still both considered bell-shaped. This one's just a lot more tighter to the mean, okay? Okay. Oh, that's that for this section. So for homework, now, I can't remember off the top of my head what I gave you already.
Well,
was it 1 through 12?
You gave us on page 116, number 1, page 117, 2 and 3,
page 119, 4 and 5, page 126, 11, 12, 15, 16, 19 through 24, 29 and 30, 35, 38, and 42.
Okay, I was all over the place, wasn't I? So I'm going to be lazy and just say now on page 126, I know you've already done some of these, so I'm going to finish it out. So this is 3.3, no, 3.2. So I'm going to want you to do 11. I know I've already asked you to do some of these, but 11 through 11 through 34. I know I've already told you to do some. That's fine. You don't have to repeat. And then
I produced all of them.
45 through 45 through 59. Now this part you can do the odds and then just do the even if you want, if you need a little more work. This one I would do the odds first, and if you understand it, go on. If you need a little more work, do the evens as well. Okay, so you can say odds for both if you're getting it. If you get done with 11 through 34 and you're not getting it, so go back and do the evens, and then I can go over the answers for those sections. It's not a big deal. Okay. Okay. So 11 through 34 and then 45 through 59. And now we're going to go on to 3.3. We got time. Oh, we'll review next. If we don't have enough time here, we'll go on. We'll finish it up on Wednesday. So 3.3 is still measures of position, but it's in a weird way measures of position of spread. We'll see what I'm talking about here in a second. But we're going to use a lot of information we're about to go over in 3.3 throughout this class. And we're going to build on it actually. So I need you to really kind of pay attention to this and see what's going on. So in 3.3, the very first thing your book goes over is z-score. Okay? Z-score. Now, to use z-score, first off, we have to have a population. It's got to come from population data, okay? It's got to come from population data. And what the z-score tells us is the number of standard deviations from the mean. That's what it pops out. The number of standard deviations from the mean. And we know already from the empirical rule, man, if you get like above three standard deviations from the mean, you're really high in that percentage, right? You're really high in those percentiles. If you get below 3 standard deviations, you're really low. There's a low chance of that happening, right? A very low chance of that happening. And so there's a very low chance of being above three percentiles. So keep that in mind as we go along here. At first, we're just going to do some basic examples. And, oh, sweet. Oh, we're going to keep this. I need to know this. This is on page 134. First example, a National Center for Health Statistics study states that the mean height for adult men in the U.S. is 69.4 inches, okay? With a standard deviation of 2.8 inches. Who is taller relative to their gender? A man, wait, we don't know the females. I guess I have to go back and get the females. Let's not worry about that part. Let's just find the z-score. For a male, that is, let's do, what is 6'9"? Is that 5'9"? So let's say we've got a 6 foot person. So that would be 72 inches.
Where'd you get the 2.8 inches? Wouldn't that be 3.1?
Oh, it tells us both of them. Thank you, Lori. You are correct. Okay, that's where it tells us. So let's look at males. So we're just going to look at males for this first example. So we've got a population that of male United States males. The average is 5'9" and a half inches almost, so 69.4 inches. And then the standard deviation is 3.1 inches. I want to know the z-score for a male that's 72 inches. Okay. So I didn't even give you the formula yet, did I? The z-score looks like this. You take whatever the actual score is. So for us, the male's 72 inches. Okay. That's going to be what we put there. We subtract it from the mean. And then we have to make it relative because it's the number of standard deviations from the mean. So we're going to divide it by the number of standard deviations. So it's x minus mu all over sigma. So x minus the population average all over the standard deviation. So our x value for this one, it's 72. Okay, 72 inches. Minus, now the average is 69.4. And then we've got to divide all of that by 3.1 inches, right? So I'm going to take the calculator out. I'm going to subtract, well, I can do this in my head. 72 minus 69.4 would be 2.6 inches, right? Divided by 3.1 inches. Do this in the calculator. 2.6 divided by 3.1 is 0.84. I'm going to round to 2 decimal places. 0.84. Now there's no units here. Actually, it's the number of standard deviations. The inches on top and the inches on bottom cancel. So what we can say is that 72 inches is 0.84 standard deviations above the mean. We know the mean, right? 69.4 inches, okay? 72 inches. Hey, look, you know what? If it's only 0.84 inches, I'm going to go back to kind of this empirical rule. If it's only, I'll kind of keep that in there. If it's only 0.84 inches, you know what? Let's just draw another one of these. Remember, we know that one standard deviation up, we know this is one standard deviation up 68%, right? Here's the mean. We got one standard deviation up and down. Look, 72 inches lies within that bucket, right? I mean, we're pretty average. If we're 6 foot in the US, that's not too far from the actual average, right? So you're not that, I hate to say you're not that special, but you're not that tall really if you're 6 foot compared to everybody in all the US males, okay? You're not that far from the standard deviation. You're somewhere about right here, right? You're somewhere right back. I mean, you're above the average, but you're not that far above the average, okay? So let's do another height. Let's say we do, what's LeBron James' height? I'm gonna Google it real fast. LeBron James' height. LeBron height. 6'9". LeBron James is 6'9". So 6'9" would be 72 plus 9. So LeBron is 81 inches, right? Ooh, let me get there. LeBron's 81 inches tall, okay? 72 would be 6 foot, and then really plus 9, so that would be 81. So 81 inches is LeBron's height in inches. Okay, so we want to know, let's find LeBron's z-score, okay? So remember, bring it down a little bit. Remember, it's, you take the actual height of the data point, minus the average. We know the average male is 69.4, and then we're going to divide it by the 3.1 up here, right? 3.1, because that was the standard deviation, the population standard deviation. Okay, so let's see. 81 minus 69.4. I should do this in my head. This is a Monday. 11.6, and then we're going to divide it by 3.1. I get 3.74 if we round. 3.74. So what we can say is LeBron's height is 3.74 standard deviations above the average US male height, okay? The average height of 69.4 inches. Okay, so now let's think about this. If we think of that whole empirical rule, if we had the entire US population, it is going to look like this, okay? There's not a lot of LeBrons, height-wise, right? And player-wise. But so we've got, in the middle, we've got 69.4. And LeBron is out here 3.74 standard deviations away. So if I just ticked off standard deviations, there's one standard deviation. There's two standard deviations. I know that's 95% of my data, right? 95% of my data lies within two standard deviations. He is above 3 standard deviations away, right? I mean, he's out here almost 4 standard deviations away. He is like right there, okay? Now remember, like the 6 foot dude is like right here, right? I mean, relative wise, he is so much taller than the average male, right? 6'9" is so much taller than the average male. A 3.74 standard deviations away is so rare. We know within this entire, if I drew kind of this entire red area here, we know only 2.5% of people, or males, I should say, 2.5% of males even lie within this red bucket. Okay, and I don't know what that is. We can do that if we want. Okay, you know what? Just because I'm curious, I want to know. If I took 69.4 and I added 2 standard deviations. Remember, 3.1 was the standard deviation. That's 75.6. 75.6. Now remember, that's 72 is 6 foot. So that's really like 6'3.6 inches. Okay. Oh, 6'3.6 inches. Okay, whatever. So LeBron, so if you're above 6'3", you're already really above 6'3.5", roughly. You're in the top 2.5%. LeBron's over here at 3.75%. That's pretty crazy. Okay. Now, just to get the other extreme, let's look up Danny DeVito's height. I know he's pretty short. And he's hilarious. Danny DeVito. I bet it's the first thing that pops up when I. Oh, 4'10". Oh man, he is short. Okay, Danny DeVito. I'm going to use this to show Danny DeVito's height too. So Danny DeVito. Now 4'10" would be 60 minus 2 inches, right? So that is 58 inches tall. Is that right, guys? 4'48" plus, yeah, 58 inches tall. So if I wanted to find his Z-score, I would say it's 58 minus 69.4 all over 3.1, right? So 58 minus 69.4, that's going to be, yeah, it's almost symmetric, minus 11.4. Now it's negative, that finds. The negative means it's below the mean, okay? So we're going to have a minus sign if our data point is under the mean, you're going to have a negative. So divided by 3.1, we get negative 3.6. I'm going to round to 8. Okay, negative 3.68. Hey, this is almost symmetric to LeBron's height. That's kind of crazy. I made these up, guys. I didn't think about this before I got started. So what this means is Danny DeVito's height is 3.68 standard deviations below the average male height. of 69.4 inches. Okay, so let's think about this. Where does Danny lie on this nice empirical? Okay, so we'll use blue for down here. So remember, here's the average, right? So he's 3.68. So 1, 2, 3.68. He's about right there. He is definitely in the lowest 2.5% of people. There's Danny DeVito. And then there is LeBron James. Okay. I mean, I'm right at 6 foot. So that would be 70. I mean, I'm somewhere in here. Did we do 70? Oh, we did 72 inches. So I'm right here, which I feel like I'm pretty tall compared to a lot of, I'm not ridiculously tall, but I can tell I'm taller than the average, right? Okay, so now here's what I want you to do. I want you to find yours. Now I got it, Lori, I know there's some other females in the class. So let's put this down. So for males, this is for males, 69.4 inches, and the standard deviation was 3.1 inches. That's for males. For females, it's 63.8 inches with a standard deviation of 2.8 inches. So that's females. So I want you to find yours real fast. I can't pause YouTube Live, so I'm just going to let it roll. I want you to find yours real fast, just as an example. It doesn't matter. Just kind of know approximately you shouldn't be above LeBron James, right? And you shouldn't be below Danny DeVito. But find yours. I'll give you a minute.
Okay, if I'm correct on mine is 0.07.
And that's what you should kind of be around, right? Unless now the other two, Coulter, and then is Nathan, is that you, buddy? The West TV. I'm not sure who that is.
Yeah, it's me, Nathan McGee.
I thought it was you. And I'm not sure about you two guys, how tall you are, but you're probably close to the mean, right?
Yeah, I'm like 5'9".
Yeah, exactly. So you're really close to the mean. So I mean, it's just rare to have somebody that's just totally outside the mean.
Yeah, I'm 5'4".
Yeah, and so you got to think like 5'4" is super close, right? Because this is 5'3.8", right? Okay, now let's do something though that talks about relative. Let's look at Brittany Griner, who is in the WNBA. Okay, and I want to see if relative wise, if she's taller than LeBron relative wise. Okay, so Brittany Griner height. Holy cow, she's 6'8". That's crazy. Okay, so Brittany Griner, I'm going to spell it right. So Brittany Griner is 6'8", which I can already tell you is going to be higher relative wise But let's find hers. Holy cow, for a female is nuts. So 6'8" would be
72.
plus 8.
72.
80
yeah,
inches?
plus 80 inches.
Yeah, 80 inches. So now she's female though, so we've got to use these numbers, right? So Brittany's Z-score is going to be 80 minus 63.8 all divided by 2.8, right? Holy cow, this is going to be crazy.
.785 or 6 rounded up. Or
Let's do two decimal places.
5.79.
Yeah, 5.79. Holy cow. Now, I'll tell you, we're about to talk about this in a few seconds. This LeBron, Brittany, and Danny, they would all be considered outliers, right? I mean, if you're trying to get the average height of a group of people and all three of those people, any of those three people showed up in your group, you're going to go, oh, crap, this is going to skew it, right? So they're all considered outliers. Yeah, Brittany's 5.79 standard deviations away from the average female height, which LeBron was only, what, 3.7? I mean, so yeah, relative wise, Brittany's a lot taller, okay, than LeBron, which is kind of interesting, okay? Okay, great. So now let's go on to the next part. So that's the Z-score. It deals with really the standard deviations from the mean. And then now I'm going to kind of turn us back because the Z, I need you to kind of grasp that Z is based on the mean, right? Z-score is based on the mean. Now we're going to turn our attention to quartiles and percentiles. They're going to be based on medians, okay? So Z-score is the mean, and now we're going to move to quartiles. What time? This class gets out at what, 10:40? I got to remember that. I don't want to go too long here. 10:40. So quartiles. Now quartiles, what's nice, they can be found in your calculator. Pretty easy, actually. It's that same one variable statistics. When you hit that, it'll pop out quartiles. I'm going to give an example that we don't have to use a calculator for first. But I need you to understand that quartile 1 is just the bottom 25% of data, okay? Quartile 2 is really where the data is split in half, the middle 50% above and below, okay? So it's the middle, and then quartile 3 is the top, really where the top 25% of the data occurs, okay? So let's look at scores, and I'll kind of just show you, and I'm going to lay these out in order, which makes it a lot easier. Now, I'll tell you, quartile 2 is also your median, okay? Quartile 2 is just your median. So if we look at scores, let's say we had a 45, a 50, a 57, 60, 65, 69, 72, 78, 80, and then an 86, okay? So if you want to write all those down, 45, 50, 57, 60, 65, 69, 72, 78, 80, and 86. And we're going to just find the quartiles, okay? We'll make a box plot out of it here in a minute, but for now, we're just going to find the quartiles. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've got 10 tests. The very first thing actually you need to find is quartile 2, the middle, okay? If I've got 10 tests, that means I have 5 below and 5 above. So it'll be a little easier, right? So 1, 2, 3, 4, 5. I'm right here. So 1, 2, 3, 4, 5. So what we would do is if the middle number doesn't, or the quartile 2, the median doesn't occur on the number, remember we take the average of the two numbers next to it. So I'm going to do that on the side here. So 65 plus 69 divided by 2 should be 67, right? 65 plus 69, yeah, divided by 2. is 67. So that's our quartile 1 or quartile 2. So quartile 2 is 67. Okay. And what that means is half of our data lies below it, which is true, and the other half lies above it, which is also true. Okay. And then to find quartile 1 and quartile 2, we're going to look at this bottom group and do the same thing. What's nice is we have 5 data sets. So our quartile 1 winds up being 60 or 57. Okay. 57. So 25%. Now this one's goofy because we don't have a bunch of data. So I know it's not exactly 25%. It's 20% because in a weird way you split this 57. I don't want you to worry about that. But what we know now is quartile 1 is this 57. And then we're going to do the same thing for this top. So all 5 of these coordinates. Oh, there's 5. The middle is 78. So that's going to be quartile 3. Okay. We found our quartiles. Your book goes over a way to find it, but we're going to use the calculator. Okay. And it's going to be that one variable stat button that we've been using all along. The examples I'm going to do in the book are already going to tell us that stuff. So I'm not going to go over it again in the calculator. If you don't know how to do it, go back and watch the chapter 3A video, and we go over how to do the one variable stat a few times. So let's look at an example. Computing quartiles. So, well, I'm not worried about computing them. Let's use them. Okay. I'm going to skip over percentiles in your book, and I'm going to come back to it. Hold on. And so I'm going to go now to the 5-number summary, which is on page 139. So I'll get back to percentiles. But for now, we're going to go over this 5-number summary. We need the 5-number summary because it leads to the box plot. So the 5-number summary, you're going to need the min, you're going to need quartile 1, quartile 2, which is our median, quartile 3, and the max. Okay. And from this, we can make a box plot. Now, your min and max might be outliers. We're going to show how to determine that here in a little bit. But for now, we're just going to use these to make a kind of a basic little box plot. And I'm going to use that example that we just did above. Okay. So our min is 45. Our quartile 1 is 57. Our quartile 2 is 67. Quartile 3 is 78. And our max is 86. Okay. And we're going to make a box plot based off these 5 numbers. And I'll kind of show you how this looks, and then we can interpret other box plots. So for a box plot, first off, you need a horizontal line with numbers. Okay, we know our minimum is 45, our maximum is 86. So I'm going to start with 40. Okay, and I've got to go up to 90. So let's see here, 50, 60, 70, 80. Let's say 90 is about right there. I shouldn't have made that arrow so close. And what I'm going to do with the quartiles, I'm going to make vertical lines. So 57 is roughly about right there. Okay. 67 is roughly about right there. And then 78 is roughly about right there. And what you're going to do is you're going to make a box around that. And what that box represents is the middle 50% of our data, right? Remember, the first quartile, there's 25% less, or 25% of our data is under the first quartile. The other 25, there's 25% of our data above the third quartile. So that means 50% of our data lies within here. And each box represents 25% of the data, okay? Now for our min and our max, we're going to do just a dot. So 45 here, 86 about right there. And then we're going to extend the dot to the box. This is why it's called sometimes a box and whisker plot. Okay, box and whisker plot. Boom, we have made a very basic box plot. This is kind of nice symmetric data too. look, each little section contains 25% of our data, their quartiles. It kind of gives you a rough estimate of where the quartiles are located. And it's based on the median. We don't know the mean of this data, right? We don't know the mean. If it's nice and evenly distributed, it should be close to the median. And this looks like it's kind of nicely distributed. So it should be somewhere close to the median, okay? So let's look at another example. Let's look at, and I like the example at the bottom of page 139. It talks about, presents the number of students absent in a middle school in northwestern Montana for each day in January of a recent year. Construct the 5-number summary. So if you look at this example, it gives you like January 2nd, there were 65 absent. January 3rd, there were 67 absent. January 4th, 71. So let's say we put it into our calculator, we do the one variable statistic, and we get this out. And we're going to pull the min, which winds up being, I'm just going to look at the data. Is it like 45 or 41? The minimum winds up to be 45. Quartile 1, which our calculator will tell us, is 45. The median, which our calculator will tell us as well, is 51. Quartile 3 is 59. Now the max, though, which is crazy, look how far the max is from these, is 100. Okay, so this is going to be a good example of data that's probably not that symmetric. So let's plot this on our data. If we wanted to make a box and whisker plot, let's plot this out, okay? So I've got to go 40 to 100. So 40, let me make these a little tighter. 50, 60, 70, 80, 90, 100, right? And I know my minimum's 41, so I'm going to make just the dot there. Actually, I have to get a marker that hasn't been used as much. So 41's right there. My largest is 50 or 100. 45 is right there. 51, right there. 59 is about right there. Look at that. Holy cow. Woo. Get to the dot. Look, something crazy is going on with this data. Okay, think about it. 50% of our data lies between 45 days and 59 days, right? So the majority of days missed, or students absent, I should say, is between 45 and 59, okay? Really, or less than 59 if you want to put it like that. Like 75% of our days are less than 59 people absent. But then we've got this big gap here. And if you look at the data, just look at page 139 real fast if you can. Hold on, if I can kind of put it up here. If you look at this data, I know it's hard to tell with this camera, but 100 it looks like an outlier. I mean, 100's a big number, 77 is a big number as well. I mean, you could even say 67, right? 67 is a big number, so 71. But this 100 just sticks out like a sore thumb. Something must have happened, right? Something, I don't know. That's not, as the statistician, we're not supposed to deal with that. We're just dealing with what actually happened, okay? Not why it happened. That's another class. Okay. So it feels like this is an outlier, and it's really making the data skewed. So really what we have, if we think of this, if we wanted to graph it, like with how we, before, it would look something like this, right? Remember, this is right skew. Right skew. Okay. So we've got to go over how to find outliers in this situation. And the way you find outliers, that is actually on page 141, because I really think 100 is an outlier, okay? There's a basic rule about finding outliers, and it's called the outlier boundary. Holy crap, I'm almost out of time. Okay, guys, hold on. It's 10:40. How about I'll finish this at the beginning on Wednesday. So on Wednesday, 3.3, I've got to go over outliers. I think in percentiles. I think that's it. Yeah, outliers and percentiles. And we'll finish up. Both those things won't take long. And then we'll review for the test. Okay, so for homework, if you go to, let's say where chapter 1 starts, or section 3.3 starts. It's on page 135. Yeah, perfect. I want you to do 1 through 3. And then page 139. Yeah, 4 through. Now, don't worry about the percentile question on these. We'll go over that. So like 4C asks, you know, Fred got a 73 on the exam. What's the percentile? Don't worry about that. We'll go over it. And the same with C and D. Actually, just do number 4. Yeah, just do number 4, part A and B. And then, does it go? So page 1, hold on a second. I skipped something. 4, 5, 6, where's 7, 8, 9? Oh, there it is. So page 142, I want you to do part A, and then we'll do B through C next. And then page 146.
On 142, you might want to put the question number
Oh
7.
yeah, with the 7.
Yeah.
Page 146. Gosh, I want to get some in here, but it's, you know, we might just wait to do all this till after the homework, till I get done with these 2 things, because it's all just thrown in there. So, and you'll have some time to review, time to go over it before the test, and you can ask me questions. But if you want to look at this homework and just pick out the ones on page 146 that talk about quartiles or talk about z-score, I would do those on page 146. And then when I finish up outliers and percentiles, you'll see they kind of put everything together in here. So it's hard to kind of pick and choose. So I'll finish that up, and then I'll give you the homework